Hello, my name is Erica Huynh, and I'm a postdoc researcher in the Multimodal Interaction Lab, which is supervised by Catherine Guastavino. I will be sharing my work on the perception of blend in space to better understand how the spatial separation of instrument sounds can influence how well they blend. Let's set the stage. Assume you are attending a live performance with these instruments on stage. At various moments in the piece, some instrumentalists might have to blend together to sound like a single entity. Where they are positioned on the stage might influence how the audience members perceive their blend. Blend describes the fusion of multiple sounds into a perceptual unity. You can have various degrees of blend that range from poorly to well blended. Sounds are poorly blended when they are playing at the same time and you can't help but hear them as separate sources. Sounds that are well blended are those that are playing at the same time and heard as a unified source, such that the constituent sounds cannot be disentangled from one another. In simpler terms, when sounds are poorly blended, you hear multiple sources at the same time. When sounds are well blended, you hear a single source. Although blend can exist for more than two sounds, for the purpose of this presentation, I will focus on the blend between two instrument sounds. Research on instrumental blend is not unfamiliar to the field of music perception. An abundance of previous studies has focused on timbral blend, pointing out the acoustic properties of sounds that can influence how well they blend. Two frequently mentioned acoustic properties are the spectral centroid and the attack time. Spectral centroid is the energy concentration of a sound's frequency spectrum, and its perceptual correlate is auditory brightness. Sounds can vary from dark to bright. The attack time characterizes the onset of the sound. Sounds can have longer attack times, much like those of sustained instruments, or very short attack times, such as those of impulsively excited instruments. It has been widely found that sounds perceived as darker and sounds with longer attacks tend to blend better. More recently, a study by Thilikan and colleagues has looked at how the parameters of the room acoustics can influence how well sounds blend. These room acoustic parameters primarily describe the reverberation, such that sounds might have longer or shorter reverberation times. These researchers found that longer reverberation times promote better blending. The studies mentioned so far have primarily presented sounds to listeners over headphones or stereo speakers. So, our contribution to the ongoing research on instrumental blend will investigate whether the spatial separation of pairs of sounds can influence their degree of blend. We selected our sound pairs from a previous study by Drew and McAdams, which asked participants to rate pairs of 14 instrumental sounds on a scale from not at all to completely blended. We aimed to select pairs that were rated similarly between the musicians and non-musicians of their study. Because we used a similar rating scale in our study, we selected two pairs that would be expected to have ratings toward each of the extreme ends of the scale. We selected the flute bell pair and the oboe trumpet pair to respectively fall on the extreme lower and higher ends of the scale. We also chose two additional pairs, each comprising two sustained instruments, that had ratings between the two extreme ends. These were the clarinet tuba and violin bassoon pairs. For simplicity during the rest of the presentation, I may refer to the flute bell as the low blend pair, the clarinet tuba and violin bassoon as the medium blend pairs, and the oboe trumpet as the high blend pair. Let's have a listen to each of these pairs from low to high blend. As you may have heard, the sounds had been matched for loudness, pitch, and duration. We presented the sound pairs to listeners in a multi-channel array of 16 speakers at ear level in the Performance Research Lab at Kermit. Here is an overhead view of the multi-channel array. Speakers are equally spaced with a radius of 3.3 meters. Listeners were seated at the center of the room and each sound pair was presented concurrently in two speakers within two general configurations. The first configuration had one sound presented at the front, and the other sound was concurrently presented in any one of the 16 speakers, including the front. The degrees of separation between the two sounds with respect to the front are indicated on the diagram. Negative degrees mean that the non-referential sound is presented toward the left. Positive degrees mean that the non-referential sound is presented toward the right. And 180 degrees mean that the pair is presented in the front and back speakers. The second configuration was where one sound of the pair is presented at the right, and the other sound is presented at any one of the 16 speakers, including the right. The non-referential sound was presented toward the front at negative degrees of separation, toward the back at positive degrees of separation, and 180 degrees indicates right and left separation. So, for a given trial, the participant might hear a sound pair presented in these two speakers, and then they would have to rate the blend of that pair on a scale from not at all to completely blended. This would repeat for each pair, in each configuration with a front and right reference, in a random order. We recruited 20 musicians and 19 non-musicians who differed in the average number of years of musical training. We wanted to see if these two groups would differ in their sensitivity to the spatial separation of the sound pairs. For the analyses, we wanted to test the effect of these 4 factors on blend ratings. We had 2 participant groups differing in their musical training, 4 pairs with various degrees of timbral blend, 2 reference points, and 9 degrees of separation. We collapsed the ratings for each degree of separation across both the negative and positive directions for each reference point, as we did pre-analysis checks that showed little to no difference between the ratings regardless of the direction of presentation of the non-referential sound. Let's first look at the musicians' ratings for pairs presented with a front reference point. This graph shows the blend rating on the y-axis, degrees of separation on the horizontal axis, and the sound pairs are represented by different colors. So, 0 degrees of separation means both sounds were presented at the front. 90 degrees means that one sound is at the front and the other is at the left or the right. And 180 degrees means front and back separation. Right off the bat, we can see that the blend ratings of the medium blend pairs are most sensitive to spatial separation, and the ratings are highest for 0 and 180 degrees of separation between the two sounds. This can be explained by the front-back confusion, which describes that it's difficult to distinguish between sounds coming from directly in front of or behind a listener, as they would arrive to both ears at the same time. Consequently, sounds presented at the front and back speakers might actually be perceived as coming from the same direction and as blending better. Let's take a closer look at the ratings for the clarinet-tuba pair. We conducted pairwise comparisons between each of the degrees of separation and 0 degrees of separation to see at which point are the ratings significantly lower. We find that the ratings become lower when the non-referential sound is presented at these speakers. For the violin-bassoon pair, the ratings decrease when the non-referential sound is presented at these speakers. So, the degrees of separation between the two sounds at which blend ratings decrease is slightly narrower for the violin-bassoon pair than for the clarinet-tuba pair. Comparing musicians with non-musicians, we see that for the musicians, the ratings of the medium blends and high blend are more spread apart, whereas for the non-musicians, ratings for these pairs are more clumped together. However, if we just look at the clarinet-tuba pair, we see that there is an effect of spatial separation on the ratings for the non-musicians, but this effect seems to be weaker and less pronounced than that of the musicians. Now let's look at the ratings for the right reference point. This time, 0 degrees of separation means that both sounds are presented at the right. 90 degrees means right and front, or right and back. And 180 degrees means right and left. Overall, for the medium and high blend pairs, ratings generally decrease with increasing degrees of separation. Ratings for the low blend pair also exhibit this trend, but it seems to be much weaker. Focusing just on the clarinet-tuba pair and looking at pairwise comparisons between each degrees of separation and 0 degrees, the ratings decrease beyond 67.5 degrees of separation between the two sounds. Ratings for the violin-bassoon pair decrease when there is at least 90 degrees of separation between the two sounds. Additionally, there should be at least 112.5 degrees of separation between the oboe and trumpet for this pair to be perceived as less blended. You may have noticed that there wasn't an effect of spatial separation for the oboe-trumpet pair with a front reference point, but there is now with a right reference point. This might be because with the right reference, the non-referential sound surpasses the midline point, giving rise to a sense of lateral separation because now the two sounds are no longer in the same hemifield. Comparing the musicians and non-musicians, once again we see that the musicians' ratings for the medium blend pairs are spread apart from the ratings for the high blend pair. The non-musicians' ratings for the clarinet-tuba pair become a bit spread apart from the other two pairs, but only at larger degrees of separation. So, if we focus on the non-musicians' ratings for the clarinet-tuba pair, the ratings generally decrease with increasing degrees of separation. But this trend is once again less pronounced than that of the musicians. In summary, to answer our research question of whether the spatial separation of sounds influences how well they blend, it seems to depend on the level of musical training of the participant as well as the pair of sounds. For musicians, the perception of the low blend pair is not influenced by spatial separation, whereas the medium blends are. For the high blend pair, there needs to be over 90 degrees of separation from the right for spatial separation to affect blend perception. Overall, we see that going from medium to high timbral blend, the sensitivity to spatial separation tends to decrease. The non-musicians were only sensitive to the spatial separation of the clarinet-tuba pair, but not of any other pair. You might be wondering why non-musicians were not sensitive to spatial separations of the violin-bassoon pair, which is also considered a medium blend pair in our study. We speculate that perhaps the non-musicians might have actually perceived this pair to sound quite similar to the oboe-trumpet pair, and therefore perceived it to be a high blend pair. Recently, we have just piloted a follow-up study where we replicate the experimental design in 2 room acoustic settings. As seen on the left, the curtains are out and the banners are down, which allow for more sound absorption and a drier acoustic condition. On the right, the curtains and banners have been put away to simulate a wet acoustic condition. Please stay tuned in the near future to learn about the findings of this study. So, we have a very clear understanding from many previous studies about how the acoustic properties of sounds can influence blend perception at the timbral level. More recently, we have also learned about how parameters of the room acoustics can impact blend, although this area will need further investigation, which we aim to contribute to. Now, in the current study, we have seen that blend is also influenced by spatial separation. Combined, these 3 perspectives create a more holistic or fused understanding of blend perception. Let's reset the stage. We hope that the findings of the current study can be useful for composers, conductors, and performers in considering where instrumentalists or loudspeakers should be positioned in ensemble and mixed music settings. For example, instrumentalists can be placed closer together if they are meant to sound more blended at moments of the performance, or they can be placed further apart if they should sound more like distinct entities. These considerations can therefore enhance the desired perceptual outcomes for audience members. Thank you for tuning in to my presentation. I am happy to take questions following the live stream or over email or in the comment section.